Hello guys, let's have a quick review on single phase AC circuits. Here is a circuit with a supply voltage of Vm sin omega t, and here is a load which can be a resistive load, an inductive load or a capacitive load. And what is this Vm sin omega t? This is the instantaneous value of voltage, that is Vm sin omega t. We can infer many things from here, that is Vm is the maximum value of your voltage which is given to the circuit, and omega is the frequency of the AC signal. So if this is the graph of the sinusoidal wave, this indicates the maximum voltage Vm, and number of cycles, this constitute one cycle, and number of cycles per second will give you the frequency. So frequency is 1 by t, and omega is actually the angular frequency, which has the formula omega equal to 2 pi by t or 2 pi f. The unit is radians per second and the frequency has the unit hertz. Similarly, you can have the instantaneous value for the current also. It is then Im sin omega t, where Im is the maximum value of the current and omega represents the angular frequency of the signal. Next is the effective value or RMS value. I have done a detailed video on this behalf. It's also called as RMS value, that is root mean square value. The RMS value is the equivalent DC value of the signal, that is if this is your sinusoidal signal, and the VRMS for this full wave sinusoidal signal will be Vm by root 2, where Vm is the maximum voltage. Similarly, if it is current, then it is Im by root 2. This is for the complete cycle of your sine wave. And similarly, the rectified wave, that is when we turn this negative part to upside, we will get the full wave rectified form of the sine wave, and this will also have the RMS value as Vm by root 2. And for the half wave rectification, if the voltage, see everything indicates the voltage as the x-axis and time is the x-axis. V is the y-axis and t is the x-axis. So for the half wave rectification, the RMS value Vrms is Vm by 2. So these all values indicate the effective value for the circuit. That is, if a DC source is given to the particular circuit, what is the result that we obtain? That DC equivalent value is actually represented by this RMS value. Detailed video is given. Next is average value of or DC value. Again, for full wave sine, V average is equal to, or V DC is equal to 2 is equal to 0, because while we get the area of this one complete cycle, everything cancels off and average value will be 0. But for a half cycle or for a fully rectified sine wave, V average or VDC is equal to 2 Vm by pi, where Vm indicates the maximum. And for half wave rectification, the V average value or VDC value is Vm by pi. Now the form factor, which is actually the ratio between RMS to average. So again, so for full wave rectification, VRMS is Vm by root 2, which is in the other page, divided by the average value is 2 Vm by pi. Solving, you get 1.11. And for half wave rectified sine wave, you will have Vm by 2 divided by Vm by pi, which is pi by 2 value, which comes about 1.57. Next is peak factor. This is also the ratio between peak by RMS. For full wave rectification, peak by RMS, that is Vm divided by Vm by root 2, peak factor will be root 2. And for half wave rectification, it will be Vm divided by Vm by 2, which is 2. 2 is the peak factor. And now what is ripple factor? Ripple factor is the AC component in your rectified signal. See, whenever you rectify a sinusoidal signal, you will be arriving at only one side wave, isn't it? Again, you will have some ripples coming over your result. So this indicates the AC component in the available DC. So the ratio or the fraction of AC component in your resultant DC output is known as the ripple factor, and it is actually VAC by VDC. And VAC, VAC square plus VDC square under root is your VRMS, the effective value of the vector summation of your AC component and DC component. So what is VAC from this formula? It is simple, VRMS square minus VDC square division VDC. On solving, when I include this VDC inside this square bracket, it will be VRMS square divided by VDC square minus VDC square by VDC square, or it is again, what is this? VRMS by VDC or VRMS by V average. It is the form factor, isn't it? So it is form factor square minus 1. We have already the values for the form factors for half wave rectification and full wave rectifications, and it's so substituting the form factor value for full wave rectified wave will be 0.48, and for half wave rectified wave it will be 1.21. Next is the graphical representation of the sinusoidal wave. There are two ways to represent your signal graphically. Those are waveform and phasor. Waveform, that we all know, it is a simple sinusoidal wave which has the details of your frequency and the voltage or current, anything, and this indicates this is one cycle, isn't it? The time period of the cycle, and this is the maximum value. If the y-axis represents the voltage, then it is Vm. It can be also a representation for the current also. And what about the phasor? See, every detail that we get from a waveform is also obtained from a phasor diagram, and here it is the rotation of vectors actually. So this can be, the length indicates the magnitude of the voltage, and the rotation indicates the angular displacement of this signal. Just like if we start from 0 and reach at pi, and this is 2 pi, this 0 to pi to 2 pi traveling is indicated by the rotation of the voltage wave, which is done in an anti-clockwise direction. So this is the phasor form, and the length represents the magnitude. Some examples are given in the last video. And next is the numerical form or numerical form of the AC signal representation, that is rectangular form and polar form. That is A plus JB is the rectangular form, where magnitude, see, from the graphical representation we get what all? We get the magnitude, also the phase. Phase means the angle. Similarly, this magnitude and phase can be obtained from a rectangular form also, where magnitude is root of a square plus b square, and angle is tan inverse of b by a. And the polar form is magnitude and angle, the phase. Just like phi angle 30 indicates phi is the magnitude or phi voltage or phi current, phi amperes, etc. And the 30 degree indicates the phase or the position, the angular position of the particular waveform, the voltage waveform or current waveform. Examples are done in the last video. Now let's have the four representations, the graphical and numerical representations for pure R load. The graphical representation is, see, I'm going to combine this voltage and current wave, V and I, for same x-axis. So if this is the voltage waveform, then the current waveform will also follow the pattern of voltage, but with different heights, different peaks. Okay, so this indicates current and blue indicates voltage. So this indicates that for pure load, V and I are in phase. So this is the graphical representation. When we move on to the phasor representation, it is like, if voltage is this way, the current follows the same line. So it will overlap on this voltage phasor, but it will have a different magnitude. Since it is having a different peak, I should have a different length of the vector for this current. So this indicates the phasor representation of pure R load. And what about the numerical representation, that is in rectangular form it is the impedance. The impedance includes both the resistive and reactive components. Since this is just a resistive component, then Z is equal to R plus J0, and for the polar form it is Z is equal to R angle 0 degree. And this 0, what is the 0? Because there is no phase angle shift or angular difference between V and I. So it is R angle 0. Now for pure inductive load, we know that the current lags voltage in an inductive load, and if it is a pure one, it lags by 90 degree. So the figure will be, if this is the voltage, I should have a 90 degree shift for me to start the current wave. So this is the current and this is the voltage of the voltage across the inductor. Okay, so when I draw the phasor representation, if this is V, current should lag the voltage. So the current should be below the voltage phasor, and this is the current value. And since the difference is about 90 degree, it should have a 90 degree phase shift. And now when I go with this impedance, this rectangular form, Z is equal to, there is no resistive component, isn't it? So it is 0 plus J XL, where XL is the inductive reactance, and that is 2 pi FL. F is the frequency of the signal, and the polar form is Z is equal to XL angle 90 degree. Since it is a positive J here, it is positive 90 degree. Moving on to pure capacitive load. This is the voltage signal. Here we know that the current leads voltage by 90 degree for a pure capacitive load. So current leads means I should take a 90 degree before this origin. That is, let me start the current wave from this point. This will be negative pi by 2. So the current starts from here. So current starts initially and it reaches here like this. This will be the current waveform, and this separation will be exact pi by 2. Now when I go with this phasor representation, if V is drawn over here, current should be leading. So current phasor should be 90 degree anticlockwise to this voltage vector. So this indicates I, and rectangular form representation is Z is equal to 0 minus JXC, where XC is 1 by 2 pi FC, and the polar form is Z is equal to XC angle negative 90 degree. Since it is negative J, it is negative 90 degree. And now for RL load, that is a combination of resistor and inductor. This is actually a lagging load because the inductor is there. Since it is not pure, the lagging phase angle is not 90 degree, that's all. So drawing the waveform, I should actually get the waveform from this pure L load. That is, if I copy this down here, this is the voltage voltage and current representation for the pure L load. But since there is a resistive combination, then this current value will be shifting towards right. So according to the angular difference between V and I. So we do not know which angular shift it is happening in the circuit. So generally it will be turning to the right side from this 90 degrees. So for the phasor, when I go with the phasor diagram, if this is the VR voltage across the resistor and VL is the voltage across the inductor and the net voltage is V, how I should draw is, if this current is I, let me mark the I first. I is the same for the resistor and the inductor, and we know that the voltage across resistor and the current through it is in phase. So if this is the I, definitely the VR will also be through this vector. So this is your VR, and we know that the current lags the voltage in an inductor. So I lags VL. So I should be behind VL. This I should be behind VL. So VL should be somewhat around this way, which will be 90 degrees phase shift, because if we consider the inductor alone, so this will be your VL. Now for adding purpose, I make this vectors or I represent this VR here, and VL is taken from the head end of VR. So this is your VL. And the net voltage or the vector addition of VR and VL will give you the net voltage V. So this is the voltage triangle for this RL load. We know that VR is equal to I into R and VL is equal to I into XL and V is equal to IZ. So cutting the current values from here, we will arrive at the impedance triangle. That is, this is your R and here is your XL and this is the impedance. So this is the impedance triangle. Also you can get a power triangle from this. That is, power taken from the resistor, or the consumed power is always across the resistor. See, resistor only gives the power output to the consumer. So that is the true power which exists across the resistor. So true power is over here, which is indicated as P. And the reactive power is across the reactive component, which is the inductor here. So reactive power is Q, and you know the reactive power, the duty of the reactive power or the duty of the inductive reactive power is just to store the magnetic field around the inductor. It does not deliver any work to the user. It is just meant to store the magnetic field around this inductor. So it is the reactive power. The unit is VAR, and true power has the unit W watts, and the algebraic sum of the vectors P and Q, or the net power, true power, and Q, reactive power, will give you the apparent power, which is S. So from this we have a formula: S is equal to P plus JQ. J indicates the reactive component. So this is P plus JQ, and you will have another term here coming up, that is phi. Phi is the phase angle between the true power and the apparent power. Also cos phi indicates the power factor. Power factor means the ratio of the useful power to your total power. That is, what is the useful power among reactive power and true power? True power is the effective power which is useful for the consumer. So P divided by what is the apparent power, the net power that we get is S. So P by S is the power factor, and since it is an inductor that is connected, we have a lagging power factor. And next is an RC load. That is, here I should get the waveform representation with the help of the waveform representation of the pure C load, pure capacitive load. This one. So here we can see that the current waveform starts from the negative 90 degree. So coming over here, this current wave starts from this negative 90 degree. Okay, fine. But since there is a combination of resistor, then we should expect this current wave to start from a little bit between this negative 90 degree and 0. It can just start from this point, but it should never cross this voltage beginning. Voltage begins from the origin, so it should never cross the origin. It should lie before this origin representation. So that angle depends on the R value and C value in the circuit. And when we go for the phasor representation, see, if this is R and this is C in the circuit, the VR represents the voltage across resistor and VC is the voltage across capacitor. Total you have V voltage, and I is the current. See, everything I am detailed is with the series circuit. Okay, series RL, series RC, etc. So for a series RC circuit, the current value will be the same. Now if I give I as a reference phasor, then you know that I and VR will be in phase. So if this is I, then VR will be over here. And what is the condition in a pure capacitive load? The current leads the voltage, isn't it? So the current vector, this current vector should lead the VC. So VC should be behind this I value. So I should draw VC behind this I value. So this is your VC. And now for adding purpose, for a vector addition, I make it as VR here and VC starting from the head end of VR. So this is VC, and the vector summation or the addition is your V. And now you know that VR is equal to IR and VC is equal to I XC, V is equal to IZ. From this you get the impedance triangle. Impedance triangle, when you cut off this I values, you have R here and XC going down, and this is the impedance value set. Also we get the power triangle from this. Power triangle is the true power, which is P, and the reactive power will be downwards, which is Q, or it is negative JQ actually, and the net resultant power is S, where S is equal to P minus JQ, and here Z is equal to R minus JXC. This indicates negative J. Okay, and for the previous section also it is like Z is equal to R plus JXL, and here S is equal to P plus JQ for an RL load. So this is the power triangle for RC load, and again here you have the power factor phi, where cos phi is P adjacent side P, or the true power divided by the apparent power. So for example, if cos phi is equal to 0.8, this indicates that 80% of the total power or the total apparent power is useful for the user, and rest 20% is for reactive purpose, reactive storage of electric field or storage of magnetic field, etc. So 20% reactive power is not available for the user. It is taken for the working of the load which is connected to the circuit. So always you should have an improved power factor in your system. Now next, for an RLC load which has the resistor, inductor and the capacitor, here the waveform will be according to the phase difference, etc. It will be very difficult to draw unless the angle details are given. So when I move with this phasor representation, this will be your VR, and VC will be downwards and VL will be upwards. Okay, just combining the previous phases of RC load and your RL load. This is your VL pointing upwards and VC pointing downwards. So I will combine both of the phases to get the phasor for the RLC load. Okay, so on adding it up, if XL is greater than XC, the voltage across inductor is greater than voltage across capacitor. So I can turn this VC to upside as minus VC. So this will be your VL, and the reverted thing will be your negative VC, and this is your VL. So you will be left with this much component, that is VL minus VC will be this much component, and this length, this will be drawn like this, which is VL minus VC, and this is your VR. So net voltage will be the summation of this one. For addition purpose, I just paste this VL minus VC to the head end of VR. So this is your VL minus VC, and this is your V. Similarly, you can have the impedance triangle also, that is, this is your R and this is your, instead of VL minus VC, it will be XL minus XC, and this is your impedance, that is Z, which includes R plus J XL minus XC. Here also it is just like Z is equal to R minus JXC. And again, if it is case that XC is greater than XL, XC is greater than XL, then this will be completely upside down. That is, this will be your VR and this will be your VC minus VL, and the net value of voltage, that is VR, VC minus VL, here will be your V, and the impedance triangle will be then R, XC minus XL and Z. So that was a quick review on single phase AC circuits. Now we can do many questions, MCQs, etc. in the upcoming videos regarding the single phase AC circuits. Hope you like the video. If you like the video, please do like, share and subscribe the channel. Till we meet in the next class, this is Minu signing off. Thank you and take care.